Today I will be talking on the role of next generation cosmological surveys in identifying primordial features. So before going into the details, let me first define what is primordial features. So primordial features are nothing but the scale dependent correction we get on top of the standard power law power spectrum, and that mathematically appears as shown in the slide. And depending upon the inflationary scenario or the physical model, the shape of the function, the functional form of the features differs. So as we all know that to date the best possible explanation that gives that we have for the origin of the primordial power spectrum, that comes from the inflationary paradigm. So and the which give rises to the CMB and large scale structures. And the base the easiest solution or easiest model of inflation that is known as the single field Sorrell model, that predicts that primordial power spectrum should be of the should be scale invariant, and they exhibit power law kind of structure, and that is excellently consistent with the CMB and large scale structure observations. Now one may ask that if power law form is very good at explaining the large scale structure and the CMB observation, then what is the point of studying primordial features? So in that matter we have several motivations. First of all, the theoretical model that give rises to primordial features, they carry a strong weightage similar to the single field Sorrell model in explaining the early universe. And secondly, despite that they are not statistically that much significant in comparison to the power law power spectrum, but also some of the primordial features like linear and logarithmic superimposed oscillation, they give better fit to Planck data. And furthermore, in the latest work of Hajra et al., they have shown that some of the primordial features has the capacity to solve some of the cosmological anomalies and tensions. So all these things prompt us to consider primordial features more seriously, and that is the prior motivation of behind doing these works. So now let me spend few minutes on discussing what is the origin of primordial features. So in the inflationary dynamics, if the Sorrell parameters or the background parameters like in, epsilon or eta, or even the sound speed, they experience sudden variation, sudden change, then that gets reflected in the primordial power spectrum in the form of some scale dependent function. And also, as my previous speaker Subedar I have told, that if the presence of sudden particle production in inflationary dynamics can lead to bump-like features. So that is also another physical scenario that gives rises to primordial features. Now if we try to understand a bit in mathematical way, so as we all know that the curvature perturbations are dictated by the second order perturbation of the action. And in the most relevant context, we can express that second order perturbation in this form, where the dynamical behavior of the curvature perturbations are captured within the parameter Cs and Z double prime by Z. And now and for the single field Sorrell model, that Cs becomes 1 and this Z double prime by Z becomes 2 by tau square. Now for any generic model, if we consider that it is deviating from the standard Cs equals to 1 and Z double prime by Z is deviating from 2 by tau square, and if we parameterize these two deviation with these two new parameter and we calculate the primordial power spectrum, then we will see that there will be a correction which will look like this, correction coming on top of the power law form. And for a practical flavor, if we have within this bracket term, if we have any delta function, if this function is proportional to the delta function, then this correction will lead to a normal linear sinusoidal features. And if this bracket term is proportional to some logarithmic oscillation term, then it will lead to the resonance features. Okay, but for bound feature, this is not so trivial to express these things like this way. So in my work, I have considered these three primordial features. One is surf features, and the bound feature, and this resonance features, and their shape and form appears as shown in the slide. So here our goal was to check whether the next generation upcoming cosmological surveys, be it CMB missions or the large scale structure mission, whether they have the capacity or competence to capture these signals if they are present in the primordial power spectrum. So for that matter, our strategy was to conduct the Fisher matrix analysis. So in order to do that, we have considered 3 individual fiducial model for each features as shown in the slide. For sharp feature we can see 3 different characteristic scale, for bound feature as well, and for resonance feature. And in this work we have considered 6 different cosmological dataset and 6 different large scale structure dataset. And for cosmological dataset we have considered both ground based missions and the satellite based mission. And for large scale structure experiment we have considered BO mission, cosmic survey, and cosmic sphere, as well as the galaxy clustering mission and their possible synergies. Here we can see that we have considered the synergy between the ground based CMB mission with the satellite based CMB mission, and as well as we have considered the synergy between large scale structure mission with CMB missions, and in the large scale structure mission we have also considered the synergy between the BO mission with cosmic sphere mission and galaxy clustering mission with cosmic sphere mission. So by this way we have tried to make our work so extensive, and where we found that in comparison to the Planck imposed bound, we can get much better bound on the feature parameters, and we can see that the best bounds are coming from the PICO missions, and also comparable bounds are coming from the combination synergy of satellite based and ground based CMB S4 and Code M5 missions, and this is true for all 3 features. And I have shown here only a single characteristic scale because there are too many plots. And for a better understanding, I have tried to express everything in terms of the percentage improvement, and where where we have seen that depending upon the scales, we are getting we are getting from 47 to 93% improvement in the bounds compared to the Planck imposed bounds. It is for short feature signal for CMB only, and similarly for resonance feature we are getting from 57 to 72% improvement, and for bound feature we are getting from 31 to 88% improvement. Now if we consider the CMB mission along with the large scale structure mission, then we can see that we are getting further improvement in the bounds, and as depending upon the scale, or we can achieve from 47 to 98% improvement for sharp feature, for resonance feature 57 to 91%, and for bound feature 31 to 90%. And in the next work related to features, we have kept the feature model same, and we have kept the CMB experiments intact. Only we have changed the large scale structure experiment, and here we have considered 10 different large scale structure data set to analyze that how they are improving the bounds. And here we can see that depending upon the LSS experiments, we are achieving from 56 to 80% improvement in the bounds compared to the Planck imposed bound for scale 0.03, and for scale 0.04 and 0.1 we are getting 47 to 90% and 90 to 99% improvement. And for resonance feature, we are for characteristic scale 30 we are getting from 65 to 91% improvement, and for the characteristic scale 5 and 100 we are respectively getting from 57 to 82% and 58 to 95% improvement in the bounds. And for bound feature, similarly we are getting that for 0.1 value of the megaparsec inverse characteristic scale, we are getting the improvements about 65 to 91% compared to the Planck imposed constraint, and for the scales 0.05 and 0.02 we are respectively getting improvement of the order of 29 to 68% and 51 to 86%. And I have shown only for one feature model, for one fiducial case for each feature model, to show that how characteristics bounds on the characteristic scales are improving. Here also we have found that base bounds are coming from the combination of SK2 GC and SK2 CS experiments, and competing bounds are getting from the combination of intensity mapping experiments and also the combination from Euclid and intensity mapping experiments. And just for flavor, I have shown here that if we keep aside the SK2 CS and SK2 galaxy clustering survey, we are getting on the characteristic scale and phase, we have seen that the intensity mapping experiments are improving the bounds far better than the galaxy clustering experiment compared to the Euclid CS and Euclid GC, and along with the SK intensity mapping survey. So now I would like to summarize and conclude that thing, my talk. So Here we have explored the role of next generation CMB and raster structure mission in identifying the primordial features, and where we have seen that the bounds we are getting from Planck, the next generation surveys can improve the bounds to a great extent, and where the best bounds are coming from the PICO, the strongest bounds, and the weakest bounds are coming from CMB missions. And we have also found that the synergy between ground-based mission and space-based mission is significantly improving the bounds. And when we are considering the large scale structure experiment along with the CMB missions, it is further improving the bounds, and the strongest bounds are coming from either Euclid GC or the combination of Euclid GC and CS mission, depending upon the scale and the feature model. And the best bounds we have achieved from the SK2 synergy of SK2 CS and SK2 GC mission. And we have also seen that on the amplitude we haven't found that much sensitivity from the CS missions. Okay, however, in the scale and phase factor, we have seen that they are sensitive to cosmic CR experiments. And another thing we have also studied, that whether depending upon the fiducial value of the amplitude, whether the bounds are changing, we have seen that it is immune to the variation with the amplitude value. So we can take these values consistent for other fiducial value of the amplitude. And also we have seen that if we are changing the scale and phase factor, then the constant are changing along with the variation of the scale and value of the fiducial value of the scale and phase factor. So thank you for the